Hey guys, today we are going to be doing this AP Physics rotation and circular motion free response, and I'm just going to get straight into it. So the image shows a portion of a roller coaster, and at point A, the track has a radius of approximately 3 meters. Whoa, 3 meters, and the cart has a speed of 2.2 meters per second. I don't know if it's going this way, but I'm assuming. Okay, and then the mass of the rider is approximately 60 kilos. So you're going to ignore it, so I'm just going to go straight. So it says, without manipulating equations, state whether the rider feels lighter, heavier, or the same as they normally would while standing on Earth. Well, for one, if you've ever been on a roller coaster, you know that you feel lighter in space. So we can say the rider feels lighter. But why, you may ask? Due to the fact that the force normal here is less than the force gravity. And the reason this is because the force net, which is equal to the force centripetal, which is your force normal and your force gravity, is directed inwards. And if you observe this picture right here, you see that the cart is at the top. It's not on the inside, which means that the support force is coming from the inside. I don't want to do the vectors just yet, which means that there's going to have to be something larger than the support force that'll cancel it out to continue to have the net force, the force centripetal be directed inwards. I feel like I should have started with the 3 body diagram so it would make more sense, but now we have force normal directed upwards, and then we have force gravity longer and directed inwards. And once again, so the reason that force, now I can show you, the reason that force gravity is longer, so the force gravity goes straight down, right? And the force normal, this is coming from the support of this ramp right here. But the force net, the force centripetal, is inwards. So in order for it to continue inwards, the force normal must be smaller than the force gravity, otherwise it won't continue to go down, right? It'll typically go the other way. And they also cannot be equal. Your vectors cannot be equal. Okay. Now, part 3 says, how heavy would a 60 kilogram passenger feel at point A, asking for the weight. So in order to do this, you have to start by summing your forces, because you need to find the weight, and the weight is your gravity, mg. So the sum of your forces is equal to MAC. And on the normal scale, what the scale reads is your force normal. So that's why we are going to look for our force normal here. And you'll see how we do that. So for one, the sum of the forces, we're going to talk about the vectors over here. But we know that force gravity is larger than force normal. So it's going to be NG minus force normal equals M. And then acceleration centripetal does have a formula, times V squared over R. And then this is your formula. And now if you see that you have a minus n, you can see that this equation will go to mg minus mv squared over r equals your force normal. And if you look at all these numbers right here, all these letters, you have numbers for every single one, so you can solve for your force normal, which will read your approximate weight. So m times g, 60 kilograms, they told us, and then 10 is our constant, minus m, which is our 60 kilograms again, 60 out of our velocity, they told us right here, was 2.2 meters per second times 2.2 squared, and then that divided by r, your radius, and your radius is given as 3, and that will give you a value of 503.2 newtons, and that is your answer. And now part B. At point B, the track has a radius of 13 meters, and the rider feels 4 times as heavy. So here at point B, the track has a radius, let's say 13. Sorry, I don't want to draw it because they ask for the forces. Has a radius of 13 meters, and the rider, the guy standing over here, feels 4 times his weight. Now, without manipulating equations, state whether the rider is moving faster, slower, or the same speed in point B as they were in point A. Now, this is a question that's actually not from rotation and circular motion. This should come from your knowledge of mechanical energy. So let's just get straight into it. So when we know right here, this is the max, right? Say I said this is my ground level. I know that my potential energy right here is at a minimum, right? And I know right here my potential energy is at a maximum. But I know that mechanical energy is conserved, which means that as potential energy is going down, kinetic energy is going up. And when we think about the formula for kinetic energy, it equals 1/2 mv squared. And we know that these two are constant. So it's really Ke equals 1/2 m. So if I'm talking about the change in kinetic energy, it equals, I don't have enough space. It equals Ke final minus Ke initial. But what we're really talking about is 1/2 m delta v f squared minus 1/2 m delta vi squared, if we're being real, because the mass is not going to change and the constant half does not change. So that's what you need to see here. So when they ask you at point B, are they moving faster or slower? They're moving faster due to the conservation of mechanical energy, and you can go, it says briefly explain. At point B, you don't want to go to point B, PE equals PE max. Sorry, at point A, not point B. Oh no. At point A, and Ke V equals 0. So at point, approximately 0, at point B, PE goes to Ke max. Therefore, you're moving much faster. Now, number 2 says, on the dot below, draw a free body diagram for the rider. So let's look at the picture. So here we have the rider. So the rider is on this track right here. Your force of gravity goes straight down, mg, and then your force normal is coming from this ramp, so that force normal goes straight up, and these are here. So we're going to go down. We have force gravity goes straight down. You have force normal going straight up, and that is your free body diagram. And now, part 3 asks, how fast is the rider traveling at point B? In order to do this, we're going to do a sum. They're asking how fast, so we already know we're going to be solving for velocity, right? So the sum of our forces is equal to the mass times the acceleration centripetal. We know our acceleration centripetal equals v squared over r. And then the force normal minus, because it's pointed upwards, this is pointed downwards, minus your mg equals mv squared over r, and you want v, so the force normal divided by r gives you force, let me go take it this way, it gives you, oh, actually, let me show you something before I do that. Now, this is the idea, right? But it tells that the rider feels 4 times heavier. So 4 times the weight, mg, so mass, which is 60 times 10, should equal 4x, right? We see that the force normal 4 times, it should equal this. 4 times 6 is 24. You add the 2 zeros, so your force normal equals 2,400 newtons, which is useful when you're calculating. So now, they give your force normal, 2,400 newtons minus your weight, which is 10 times your 60 given kilograms. This is your g, is equal to m, which is 60, v squared. V squared is what you're solving for, over r, which is 13. Then you do 2,400 minus 600 to give you 1,800 times 13 divided by 60, and the square root of that is equal to v. You get that v squared is equal to 30, and then v equals 19.7 meters per second. You're done. And the reason we are focusing on force normal here is because for the weight specifically, is because your scale is reading your force normal, it's reading your support force. So say somebody is standing on an elevator what the scale is reading on the elevator is your force normal. Okay. Now let's read part C. Part C. At point C, the track and cart exert a force of 400 newtons on the 60 kilogram rider. The velocity is 7 meters. First, draw a free body diagram. Oh, I didn't already hit it down. Okay, so at point C, we can see the car is upside down and the support is right here. Here's your support, and your support is actually coming downwards. With the force of gravity, it's always downwards. So for part C, you have two vectors in the same direction. Force gravity and, force normal, and then force gravity. And the reason that force gravity is larger is because you want to continue downwards. Force normal is a support force, and your force centripetal is directed downwards, so you need the gravity to be stronger. And then part 2 of the last part says, determine the radius of the track at point C. Well, we know that the sum of the forces equals MAC, and MAC equals V squared over R, which means this is our R, which means that the sum of our forces equals to this can give us our radius, which is equal to, we have force gravity and force normal, but they're both in the same direction, so it's force normal plus force gravity. And we want to solve for R, and if we say that we rearrange the equation, we'll have that R equals mv squared over force normal plus force gravity. I did this by multiplying R here and dividing this to give you this equation, and then you simply plug in mv squared. M 60, it's given. Your V is 7, it's given. It's right here. 400 newtons, 600 kilograms. Your force normal is your 400 newtons. It says the track and cart can exert a force of 400 newtons on the rider. Your G is 60 times 10, which equals 2.94 meters, and you're done.